let's imagine that you're on an airplane heading at a velocity of 110 kilometers an hour. There's a tailwind blowing at a velocity of 50 kilometers an hour, and you want to find the airspeed of this airplane. Or let's say that you're a graphic designer and you want to coordinate the optimal vector for a drawing of yours. Or let's say that you're heading out for some fun and you want to find the direction and speed to curl your bowling ball at your bowling pins in order to hit a strike. All three of these examples I've just described above are examples of real-life application of vectors. Welcome to video 9.4, discussing the meat of vectors. First, we're going to take a look at some vector basics. Then we're going to move on to algebraic vector operations. Next, we'll look at some visual vector operations before ending off with looking at angles in a vector. First, let's take a look at vector basics. So what really is a vector? Well, a vector is a quantity with both magnitude and direction. Magnitude is simply the length of a vector, and direction is simply the position a vector is heading. The vector could be graphically represented as this, where vector v, represented by this symbol, has a length depicted here and a direction represented by the arrowhead. If we dissect vector v a bit further, we can see that there's two components, I and j. The I component is the x direction of the vector, and the j is the y component of the vector. If we were to represent vector v using an equation, it would be ai plus bj, where a simply is the x component, the magnitude of the x component, and b is the magnitude of the y component. As you can see, this side of vector v is the initial side, while the side with the arrowhead is the terminal side. Vectors can have a positive or negative direction, as seen with this chart as the frame of reference. So, for example, a vector in this direction would have a positive a component and a positive b component, while a vector in this direction would have a negative a component and a negative b component. Now that we've discussed some vector basics, let's take a look at algebraic vector operations. Let's make the following assumptions with a constant c equals 5 and a v and a w vector. Take a screenshot if you need. This is some pretty important information. To add and subtract vectors, it is very simple. All we need to do is add or subtract the I component of the vector with the j component of the vector. Once you group your similar variables together, you get your answer. If we want to multiply vectors with a constant, we need to follow the distributive property. So now we've explored some simple algebraic vector operations. Let's look at visual vector operations. Assume the same variables. Visual vector operations are just representing vectors on a graph. If we want to graph vector w, all we need to do is take a look at the equation. Then, seeing that I is positive 3, we move 3 to the right side. Seeing that j is negative 2, we move down 2 units from where I left off. Our resultant w vector is then represented by this arrow. It's very similar to graphing with a coordinate plane. We want to solve an equation such as 2w plus v graphically. All we need to do is graph 2w and v using the method shown above. Take a look that the terminal side of the vector is connected with the initial side of another vector. Graph 2w and graph v, connect them together with terminal to initial, and our resultant vector 2w plus v is thus represented by this vector. Now let's amp up the level of difficulty by incorporating angles into vector directions. So far, all we've done is represent direction of a vector with an arrowhead, like this. However, that's not the case most of the time. Vector direction is often represented by angles, such as the example here, where this is the vector and this is the angle of the vector, hence indicating the direction the vector is heading. So how do we calculate a vector given its angle? Well, a vector is defined as the magnitude of a vector multiplied by the cosine of the angle of the I component plus the sine of the angle of the j component, where alpha is really any angles in degrees. So let's look at a sample problem to understand this concept further. Let's say we have a vector magnitude of 5 and a alpha of 240 degrees. What is our vector? This is a very simple problem. All we need to do is use our formula and plug in. Convert cosine of 240 degrees into negative 1/2 and sine of 240 degrees into negative root 3 over 2. Distribute, and we obtain negative 5 over 2j minus 5 root 3 over 2j. As you can see, vector operations are used on a day-to-day basis. There are so much more examples I haven't shown you today, but that is all around you in everyday life. I hope you can take away with some useful knowledge during this very short 6-minute video, and best of luck on your finals.